Hello and welcome back to Chapter 4, Managing Money. Today we're going to talk about Unit 4B, the power of compounding. So we're going to learn about compound interest. Here we go. Let's start with some definitions. The principle in financial formulas is the balance upon which interest is paid. All right, so if you have zero principal, there's nothing to charge interest on. Your principal is higher, more interest. All right, so principal is the only amount that they charge interest on, the balance upon which interest is paid. Balance, the interest is paid. Simple interest is paid only on the original principal, but not any money you make and add to the account later. Compound interest is interest paid both on the original principal and all the interest that has been added to the original. So with simple interest, simple interest, you have your stack of your principal, and then each year you get your little stack of interest. All right, interest. But with compound, you have your stack of principal, and then you add your little stack of interest. But now you're going to add interest on the original principal, and that first interest is going to add a slightly bigger amount of interest. And so now we're adding interest on top of principal and interest, and this is always how you want banks to pay you. All right, let's look at a savings bond. While banks almost always pay compound interest, bonds usually pay simple interest. Suppose you invest $1,000 in a savings bond that pays simple interest of 10% per year. How much total interest will you receive in 5 years? And if the bond paid compound interest, would you receive more or less total interest? Let's take a look. First of all, simple interest. Every year you receive the same interest payment. So you have $1,000 is your principal, and you earn 10% in interest. So 10% of 1,000 is 100. Remember, we always do calculations with decimals, not percentages. So that's 0.10 times 1,000, which is 100. So every year you receive $100 of interest. So after 5 years, you'll have a total of $500 in interest. All right, so we started with 1,000, and then we added 100 first year, and then we added 100 the second year, and then we added 100 the third year, and we added 100 the fourth year, and because I ran out of room, we added 100 the fifth year, right? But that 1,000 was all that we were ever making interest on. But with compound interest, you receive more than 500 in interest because the interest each year is calculated on your growing balance rather than on the original investment. So the first year, you have $1,000 and you earn your 10% or $100. But now in your second year, you have $1,100. You don't go back to that original 1,000. That interest goes into the account, $1,100. Now that will earn more interest because you have more money in there. So in the third year, now you'll have $1,210, and you will earn 121 in interest. So you're always earning more each year because you have more each year. So compound interest raises your balance faster than simple interest when you're saving money. All right, here's our compound interest formula for interest paid only once a year. This is key, only once a year. We're not talking quarterly, monthly, daily, continuously, semi-annually, all those different things. Only once a year. The future amount, all right, the accumulated balance, is the principal multiplied by, in parentheses, 1 plus the annual percentage rate, APR, as a decimal, never as a percentage, to the power of the number of years. All right, so if it only happens once a year, this is our formula. All right, I'm going to write it right here. P times 1 plus APR to the number of years. Suppose you invest $100 into two accounts that each pay an interest rate of 10% per year, but one pays simple interest and the other pays compound interest. We're going to make a table to show the growth of each over a 5-year period. Use the compound interest formula to verify the result in the table for the compound interest case. Okay, so let's make a table. We're going to be fancy about it. Check it out. Simple interest, right? I will have $100 invested for 5 years at 10%. So at the end of the first year, I make 10% of $100. I get $10. So I have my old balance of 100 plus my money of 110. Second year, I earn 10% on that $100 that I originally invested, that original principal. So I earn $10. I had 100 plus the 10 from last year. Now I add 10 more to it. I have $120. Each year I add $10. Each year my new balance is exactly $10 higher because $10 is exactly 10% of our principal. But with compound interest, right? 10% of $100 is $10. So I had the 100, I earned the $10. As I start my second year, right? The end of the first year, I have $110. Now I'm making 10% on my $110. So now I'm making $11. I've already made more money than this simple interest account. It's only $1 more, but that's $1. And some days, a day late and $1 short, it's nice to have that dollar. So we had that 110, and now we add 11, so we're at 121. So now we take 10% of the 121 and add it to what we have, getting a new balance of $133.10 to start the new year, and that's what we make 10% of. Notice that each time in simple interest, it's always 10% of $100. 10% of that initial amount, it's always $10. There's consistency in this. Consistency is nice. But compound interest brings growth. And after 5 years, the compound interest account earns $11.05 more than the simple interest account. All right, let's take a look at this, though. We wanted to verify this number, 161.05. Let's use our equation to verify the final entry in the table with the compound interest formula. Right, we had a $100 principal at 10%. 10% is 10 cents. And being lazy, we frequently drop off that zero, right? Significant digits and all. And then my y, the y power of 5. So this becomes 100 times 1.1 to the power of 5. Take care of parentheses. Now we'll take care of exponents. $100 times 1.6105. There are more decimals. There are not any more decimals. Use as many as you need to. Go at least 3 or 4 decimals deep on money problems. That way you could round to 2 decimals at the end if needed. Excuse me, losing my air here. 1.1 to the 5th is 1.6105. And finally, when we multiply that by 1, that's the amount that we had after 5 years on the compound interest table that I circled on the previous slide. All right, so the formula works, and we don't have to do tables of values. But we could check things out, right? How does quarterly compounding affect a $1,000 investment at 8% per year? Well, it's quarterly at 8%. There are 4 quarters in a year. There's also 4 quarters in a football game, a basketball game, and $1. But right now, all we care about is 4 quarters in a year. 8% divided by 4, that's 2% per quarter. Right? 8% interest per year, but it happens quarterly, 4 times a year. So it's like we get 2% per quarter, which should give us a total of 8% in the year. So after the first quarter, right, think about the 12 months. A quarter of 12 is 3. So the 2% of $1,000, I'll make $20. In the second quarter, now I have $1,020 in my account, and I'm making 2% of that. So this time I make $20.40 in interest. So I add that to what I have. I'm at $10.40 and 40 cents. The third quarter, now I'll make another 2% because my 8%, right, 2, 4, 6, 8, my 8% gets paid out each quarter over the course of a year. 8% distributed 4 times is 2% each. But it's growing and growing and growing quicker because I'm getting interest more often than when I just had interest at the end of the year. All right, so this is kind of how it works out. That's why we're going to be looking at this formula just a second. Here it is. The APR, the annual percentage rate as a decimal. Notice how it's formulated in annual percentage rate. So we had that 8% APR. But then we said the number of compounding periods per year, quarterly, 4 quarters happen in a year. So APR over N, in our previous example, was the 2% that we used. Okay, so for our previous example, that's how it was calculated, and that's why I pointed out that fraction and how we divvy it up. Also, instead of this being just the APR, now we look at number of compounding periods per year. Here also, now we want the total number of compounding periods. The total number of compounding periods is take the number of compounding periods per year. Quarterly, there will be 4. And then we'll multiply by the number of years. For example, if you get a mortgage, 30 years, monthly payments, 12 times 30, 360 payments to pay off your house. Right? That's exactly how it works. Here we go. Suppose you deposit $5,000 in a bank that pays an APR of 3%. And compounds interest monthly. How much money will you have after 5 years? Compare this to the amount you'd have if interest were paid only once each year. Here we go. The starting principal is $5,000 and the interest rate is APR equals 0.03. As I read through it, that's kind of what I sketch out and I write to myself as I read through. Monthly compounding, that's important, means that interest is paid 12 times a year. And we are considering a period of 5 years. So we find the values for each one of our variables in the formula, and we can substitute. Our accumulated amount will be the principal of $5,000 times, in parentheses, 1 plus 3% compounded monthly, close the parentheses, monthly for 5 years. All right, how long? Monthly for 5 years. How much interest am I getting? I'm getting 3%, but it's being divided up 12 times. So I do parentheses first. 1 plus 0.03 divided by 12 will give us 1.0025. My exponent, 12 times 5, gives me 60. Next step, I'm going to type this entire thing into the calculator exactly as it's written, and I'll get $5,808.08. Lots of 8s. For interest paid once each year, we find the balance after 5 years by using the formula for compound interest paid once a year. So now we'll just use 0.03 APR for 5 years because we're not dividing it up amongst 12 payments. All right, so these numbers don't change if we're just going yearly. And that turns out to be $5,796.37. So there's a difference, right? 3% is not as good as 3% monthly, because that 3%, whether we're earning 3% in the whole year no matter what, but we gain it more often here. And as we gain more interest each month, now we're building up our principal plus interest for the new calculation of interest. It's awesome. Compound interest, way to go. After 5 years, monthly compounding gives you a balance of $5,808.08, while annual compounding gives you a balance of $5,796.37. As I was saying, even though it's only $11.71 more, it is more, even though the APR is the same in both cases. And now instead of looking at $5,000, let's expand this to $500,000, right? And now we're looking at a difference of 579,000 versus 580,000. Excuse me. Numbers, when the numbers get bigger, the difference gets bigger, it matters more, right? $111,000 might be significant that we want to save over the course of our home mortgage. All right. Annual percentage yield, also called the effective yield. I will use this very frequently, or just simply the yield. It's the annual percentage by which a balance increases in 1 year. It's equal to the APR if interest is compounded annually. It's greater than the APR if the interest is compounded more than once a year. So I'm not going to do that. We're going to just say it here. APR is the annual percentage rate. APY is the annual percentage yield. APY is equal. All right, so the annual percentage yield is equal to the annual percentage rate if the interest is compounded annually. Put a little break here, a little space there. Annual percentage yield is greater than the annual percentage rate if interest is compounded more than once a year. All right, the yield will be larger because you get that interest more often. It builds up your interest over the course of a year more frequently and therefore more. All right, let's look at continuous compounding. Let's take a look at the end value for different. It's 8%, right? An APR of 8%. Annual percentage rate, 8%. This is annually, right? It happens once a year. It's just going to be 8%. If we're looking at, I'm going to throw down some words here too that you might want to consider. Your words will always give you your end value. So annually, compounded quarterly, here's monthly, here's daily, and the rest of these are just nonsense to show you the pattern. These ones are frequently used. I will also put here 52 for weekly is another one that we'll use. And those are the only, let me think, 1, 2, 3, 4. Yeah, those are probably the only 5 that you'll use for end values in this class. But if we use larger and larger end values, we could see that this APY settles on an 8% annual percentage rate. The more often it's compounded, it turns into 8.3%, really. It's a billion, right? A billion times a year your interest calculates. We're going to end up calling that continuous instead of something crazy like a billion. But we can see here that the annual yield, although the annual rate starts at 8%, as the compounding per year increases, the annual percentage rate gets closer to the annual percentage yield for continuous compoundings. This is called a limit. And if you're interested in things like this and how numbers get crazy close to each other after a while, or graphs like this, talk to me about becoming a math major instead of whatever major you have right now that doesn't need you to take very much math. Because if you're curious, that's all you need to be a successful mathematician. We'll get you going. Okay, compound interest formula for continuous compounding. This is what we use instead of 1 billion times it gets interest gets added per year. We can't, how are we going to split up a billion times per year? So we call it continuous compounding. This E is called Euler's number. It's a button on your calculator. It's about 2.71828. Annual percentage rate times the number of years. Here we go. A is the future amount. P is the starting principal. Annual percentage rate as we have, the number of years as we have. And E is a special irrational value that we will use straight up on the calculator. If you want to know the decimal for it, there's the start, but it's an irrational number. It has a never-ending decimal expansion. So here we go. An example. You deposit $100 into an account with an APR of 8% and continuous compounding. How much will you have after 10 years? Well, we deposit, that's our principal, is 100. 8% as the decimal is 0.08. 10 years, so what years equals 10. So if I'm looking at my calculator, what I'm going to type is 100, and then I'll use a button called second, and then it will have an LN, because up here it will have an E button. So this is the E that it's looking for. And what happens on my screen is 100, and then usually it's not true. It's not going to give me that eraser. My calculator, if I look at it, TI 84, it will look like this quite possibly. E to the, and it should prompt a parenthesis. If it doesn't, then go ahead and put that in. And then our times button, close the parenthesis and enter. All right, that's exactly how I would enter this in my calculator. Let the calculator do all of it at the same time. Personally, I can't do this in my head and multiply by 100, but the calculator's smarter than me. So after I take my 0.08 and multiply by 10 and get 0.8, I'm just typing that all in. I get $222.35. Continuous compounding. Pretty cool, but we've only gained $122 in 10 years, so the principle matters. All right, that's it for section 4B on compound interest. Thank you very much for listening.